Hi, in this tutorial I'm going to be explaining about an introduction to machine learning and neural networks. So in the first part of the talk, I'm going to be explaining some introduction to machine learning and some interesting applications we've seen in recent years. And after that I'll go on to demonstration, then a demonstration of overfitting and some demonstration of image classification. So first with the introduction and applications. So a big success of machine learning in recent years has been in problems like image classification, where we are trying to learn a predictive function, f of x, to approximate y. And so in the image classification example, where we want to learn a function f, which takes an image of a digit here. So you can think of this as a matrix of pixel intensity values, where the black values are the low values, the white values are the high values. And so it's just a matrix of real numbers, and we want a function that takes one of these matrices as input and outputs a class integer value and tells it what digit is in that image. So here f of this 0 image should result in the integer 0, f of this 1 image should result in integer 1, etc. So in this context, machine learning can be thought about in terms of inputs, features x, which can be easily computed using traditional algorithms. So in this example, that's the matrix of pixel intensities, and the outputs labels y are what we want to predict. And so typically those are easy to get by asking a human, but hard to compute using traditional algorithms. And here that's the image class, so it's the 0 or the 1 here. And here so the problem that we're talking about here is a multi-class classification problem, or 10-class classification problem. And so with traditional or unsupervised algorithms, the problem would be, I give you one of these images or pixel intensity matrices. For example, it's a matrix of 16 by 16 real numbers, and your job is to call a function f that returns one of the 10 possible digits. And so how to do that? Well, nobody really knows how to do that, so we're using machine learning instead. And so the idea with supervised machine learning algorithms is that I give you a training data set with paired inputs and outputs. So here I'm showing you a lot of examples of each of the digits from 0 to 9. And so at the top of this image, I'm showing you the corresponding labels, right? So all of these are examples of the 0 digit images. All of these are examples of 1 digit images, etc., right? So now instead of coding an algorithm that directly works on these images, and your code, it will be outputting this thing. Your job is to code an algorithm that learns this function f from the training data. So given all of these training data examples, your job is to code a function that learns this classification function f. So you're not coding the classification function directly, but you're coding an algorithm that will output a classification function. So that's what supervised machine learning does. And so the advantage of the supervised machine learning approach is that you can do this with all different kinds of data sets, regardless of what particular pattern is encoded in the data set. So, yeah, this classic digit classification problem has been used in the machine learning community for decades now. But there's a new database that's appeared in recent years called the fashion MNIST dataset on the right. And so the structure of the data is totally the same. Each example is a 16 by 16 matrix of pixel intensities, grayscale image. But so there's also 10 classes, but here the difference is that they're not digits. Here in this fashion MNIST data set, the 10 classes are the different categories of clothing. So the remarkable thing about supervised machine learning is that you can use the same algorithm to on each one of these different data sets, and it's going to learn a different classification function. So that is, you use the supervised machine learning on this digit data set, and it's going to spit out a function for classifying images into one of the 10 different digits, and you use the same algorithm on this other data set. It's going to spit out a different function for classifying images into one of the 10 categories of clothing we see here. So, so therefore, I mean, the pattern is really encoded in the data set, not the algorithm. And so this approach is really useful if we have a large database of labeled examples, but an even larger database of unlabeled examples for which we want to make predictions of the class for. Or if for some reason getting the labels is long costly. And again, so this approach is very flexible. As long as you have enough training data, you can get state-of-the-art accuracy. So continuing with the previous example, we could use some, say that we have a learning algorithm called a learn here that we've coded up, or that we've used from an off-the-shelf library. So say we use it on this first data set, it's going to spit out a function f, and we use it on the second data set, it's going to spit out a function g. So what we would expect then, after having learned these two functions f and g, is that if we use f on one of these digit images, it's going to spit out a 0 or 1 for the corresponding images. Or if we use g on a shoe, it should spit out a shoe, or if a 0 if the 0 is the shoe class, and g of this pants image should spit out pants, or 1 if 1 is the integer that corresponds to the pants class. So a question for the audience is, what happens if you do f of shoe image or g of 0 image? So that's kind of unusual because the shoe images were not seen at all in the training of f, and these 0 images were not seen at all in the training of g. So think about that for a second. Maybe you want to pause while you formulate an answer of what might happen. So yeah, essentially what's going to happen is that in both cases, the function is going to return something. So it's going to be an integer between 0 and 9 in both cases, but it's just going to be completely nonsense. So this illustrates one of the pitfalls of machine learning, and why it's not exactly intelligent. Some people like to use the term artificial intelligence. Machine learning is kind of a branch of artificial intelligence, but it's really concerned with solving these very specific problems. So in this example, like if we're showing if we're asking the f function to classify the shoe image, it's just going to spit out nonsense because it hasn't seen any shoe images, so it doesn't really know what to do. So yeah, the moral of the story is that if you want the supervised machine learning to make sense, to give accurate predictions, you have to have test data that is reasonably similar to your training data. So just a few other examples about how machine learning can be useful in different applications. There's a paper in the Proceedings of the National Academy of Sciences in 2009 about the cell profiler system, and this is super useful in biology. Again, it's an image classification problem, and the idea is that the biologist has done thousands of experiments in all of these, each one in a different well, and maybe they have a stack of these 96 well plates, and in each one of those wells they maybe have a few different images. Each one of those images you have hundreds or thousands of cells, and what they want to do is they want to quantify how many cells appear in each image according to the morphology of the cells. And so what they do is they use iterative machine learning. So instead of manually classifying each one of those cells, there's way too many to do by hand, what the system does is it iteratively shows the biologist some cells, and then they'll classify each cell as yes, this is the pattern that I'm looking for with this little budding cell phenotype over here. Or no, this is not the pattern that I'm looking for because it doesn't have that phenotype. And so after seeing a sufficient number of examples, it's the system will be able to make an accurate classification of all of the other cells that the biologist doesn't have time to manually label. So again, the input here X is image of a cell, and output Y is yes or no. Yes if it's the phenotype we're looking for, no if not. And yeah, so another example is this machine learning for image segmentation. And so here we have an image from this Label Me paper. The idea is that here again the input is an image, and the output here is going to be a category for every pixel in the image. So what we want the machine learning to do is to label these pixels as tire pixels. We want to label these pixels as sky pixels, these pixels as window pixels, etc. And so they created an interactive tool where the users can draw polygons around the things that they want to label, and to create label databases to train and test classifiers for this kind of problem. And so in this paper, they have this example figure that shows how the image segmentation works. And so the idea is that given the input image of paper cup, the algorithm will output it should output something that looks like this, where the black corresponds to the background, which is not the paper cup, and the white corresponds to the foreground, which is the object of interest, the paper cup here. And so these are all the different examples of the training data that they have gathered using this system. So the question here is, what are the types and dimensions of X, Y, and F in this example? And I'll let you think about that for a second. You can maybe pause. So in this example, it's the X, or the input, that's the one of these images. So it's going to be a matrix of pixel intensities with dimensions of the height in pixels, the width in pixels, and then the number of color channels in the image. And then the Y is going to be this binary image, basically. So it's going to be a matrix of zeros and ones, where the zeros would represent the background and the ones represent the foreground. And the F is just a mapping between those two spaces. Another example of a big success of machine learning has been in text processing. And so a good example of that is spam filtering in your Gmail. So the idea is that we want to some function that takes an email message as input and then outputs the binary classification 0 if it's not spam, and 1 if it is spam. And then so the idea is that we can create training data interactively, and that's what Gmail actually does. So if you look in one of your spam message box, you see one of these gray boxes, report not spam. If you click on that, that's going to give you that's going to add one more observation to Gmail's training data set that says, well, messages like this should be labeled as zeros or not spam. And conversely, if we have a message like this, and we click on this is a standard message in my inbox, and we're going to click on the this warning exclamation mark symbol over here. Well, that's the spam symbol, and it's going to tag that message as a one label or a spam message. So it's going to basically use this for training the future classifier that will hopefully um, predict future emails that are similar to this as spam as well. And so another example of machine learning in action is in automatic translation. So Google has gathered this huge database of scanned books, and sometimes you have text in different languages. Like here, the Count of Monte Cristo in French and the translated English version. And so when you have these pairs of text like this, you can use them to train a machine learning algorithm. So the idea is that this is a problem called machine translation, and it's implemented, and you see this in action in Google Translate. The idea is that if you put in a text in French that maybe you're not capable of reading, what we would want from Google Translate is to output the translated version of the text. And so these two images come from my favorite passage in the Count of Monte Cristo, and yeah, and so I mean, if you actually look at the real translation of this passage in Google Translate, it's not going to be exactly like this. It's not perfect, but the idea is that you can, in Google Translate, it's going to let you correct it so that the next time it sees a similar passage, it's going to be even better, right? So that's the idea about machine learning. So even if the predictions are not perfect, you don't have to change the algorithm to get better predictions. You just have to change the data, and the algorithm should be able to learn how to make better predictions based on that increased number of data. And so final example, machine learning for medical diagnosis. So again, this is an image processing example where it's described in National Geographic last year, where it shows that what we want, what the researchers did is they trained a classifier that takes these retinal scan images. So these are photographs of the eye basically, and basically we have a function that takes this as input, and it predicts all sorts of different things. So you can see in the article, you can predict which patients have high blood pressure or is at increased risk for heart attack or stroke. So it's kind of remarkable because this is an example where I guess a human expert even would have a probably difficult job of just looking at this image and figuring out which features of the image would be related to blood pressure or stroke, but maybe it has to do with something like the size of the veins or something like this. But in any case, this is an advantage of machine learning. No matter how strange the data, the machine learning algorithms will be able to pick up on some pattern and use it if it's consistent, and it's always there in those images, even if the human experts are not aware of what that pattern may be. Okay, so that's it for this section, and so please join me for the next video.